All right, so the last talk in the afternoon is Nafri from the University of Texas at Austin. And he's going to tell us about full extended three-dimensional topological filtering.
Thank you, and thanks also to the organizers. So I want to tell you about some work I'm doing currently with Konstantin Telemann. But to warm up to it, I want to talk for a little while about manifolds and algebra, in particular, how we get algebra out of manifolds. Much the same way as in algebraic topology, we get algebra out of topological spaces. So indeed, this is part of algebraic topology, and the start of the story is back in the early 40s with Pontryagin, and then in the early 50s with the thesis of René Thom, who introduced the idea of Cobordism. So if we have k-dimensional manifolds, y0 and y1, we introduce an equivalence relation. So these are manifolds without boundary, and they should be compact. So in other words, closed manifolds. And we say they're equivalent if there's a compact manifold one dimension higher, x, which has a boundary which can be divided into two pieces. One piece is y0, and one piece is y1. So this makes an equivalence relation on these compact manifolds of dimension k, and the equivalence classes are called omega k. That's called the Cobordism group. And it's a group because the group operation is given by disjoint union, so it becomes an abelian group. So there's one of these abelian groups in each dimension. And in fact, if we put them all together in all different dimensions, then there's a second operation, namely Cartesian product, and the two together become a ring. But the analog of Cartesian product actually won't appear in our talk, just in a sense in one small place. But it's really the disjoint union. So what René Thom did in his thesis is to link this up to other algebraic topology, namely he constructed a space, MO, and the homotopy groups of that space are, in fact, these abelian groups. And I didn't say what kind of manifolds these are. These might be oriented manifolds. They might have no structure, the way I said it. They might have spin structure and so on, and there are different computations for different kinds of manifolds. And these Cobordism groups play a central place in many parts of homotopy theory. For example, if we consider framed manifolds, manifolds with a, in this case, stable trivialization of the tangent bundle, then this space MO is actually replaced by the sphere, becomes a stable sphere spectrum, and these homotopy groups of the sphere are then identified with these Cobordism groups. So on the other hand, if we do complex cobordism, it has a certain kind of universal property. So what we want to do is gradually build up more complicated algebraic structures than abelian groups out of manifolds. And the first step will be to build a category of manifolds. And so here we're going to remember more information, not just identify the manifolds, but remember how they're identified. So in other words, we're going to think about these Cobordisms, but these Cobordisms are a map now between y0 and y1. So they have a particular direction. And an equivalence relation, of course, is symmetric. It doesn't have a direction. But here we're considering maps, and the map definitely has a direction. And so we want to think of a category whose objects are these, n-1 manifolds, y0 and y1, and the n-dimensional manifolds, x, are the maps between them. These are the Cobordisms. And of course, we compose by gluing. So if we have a Cobordism x, which is a map from y0 to y1, and a Cobordism x prime, which is a map from y1 to y2, if we glue together by identifying the two different copies of y1, we get a new compact manifold, and that's the composition of these maps in this category. And the category has an analog, a souped-up version of the abelian group structure we had before. That's what's called the symmetric monoidal structure on the category, and it's the same geometric operation of disjoint union. So we can take the product, if you like, the monoidal product of two y's, two n-1 manifolds is just their disjoint union, and the product of maps, again, is the disjoint union. So we again have this algebraic structure, this abelian structure. And of course, we can recover the group that we started with, this Cobordism group, by simply forgetting the detailed information about the maps and using the maps as an equivalence relation. In other words, saying that two objects, y0 and y1, are equivalent if there exists a map. And in essence, what we're doing then is inverting the maps, because we're saying every time there's a map, we're saying it's an isomorphism. We're identifying the two objects. But in the Cobordism category, it's not true that maps are invertible. So we certainly have identity maps. A cylinder is an identity map because if I take a cylinder and compose it with any other Cobordism, then the composition is just the same manifold up to diffeomorphism. So a cylinder acts as the identity. But this particular Cobordism, for example, has no inverse. That's not an invertible map. So definitely there's new information here, and the new information should be thought of as having to do with the non-invertibility. Okay. So that's enough already to tell what a topological quantum field theory is. So, well, let's let vect denote another symmetric monoidal category. This is one that comes purely from algebra, and it's a linear category, meaning that the objects are complex vector spaces, and the maps that go, the morphisms between the objects, are linear maps of complex vector spaces. So what an n-dimensional topological field theory then is simply a representation of this Cobordism category. It's a homomorphism from that algebraic structure of these manifolds to the algebraic structure of vector spaces and linear maps. So homomorphism there is the standard word in algebra we use when we have a map between two sets that preserves all of the algebraic structure. In this context, it's usually called symmetric monoidal functor, but it's the same meaning as homomorphism. So, so it's in essence a representation, a kind of homomorphic image, a linear image of these manifolds. And it's a very slick definition, and it encodes a lot of structure. And in a sense, I think of it as summarizing a lot of what we've learned about quantum field theory, just purely the algebraic structure of quantum field theory, and not just topological quantum field theories. So the same definition could be used, for example, Graham Siegel long ago wrote a paper encoding conformal field theories in 2 dimensions in a similar language, but instead of a Cobordism category of topological manifolds, it's a Cobordism category where the manifolds also have a geometric structure. So in that case, the 2-dimensional manifolds have a conformal structure. But you could imagine having a Cobordism category where the manifolds have metrics, for example. And so in that way, you could encode quantum field theories that aren't simply topological or conformal. Okay. So what is some of the algebraic structure that's encoded in that definition? Well, there's a locality which has to do with these compositions. Namely, when we glue manifolds like this, it's saying that if we take an n-dimensional manifold, we can compute something by chopping it as long as we chop along codimension 1. So in this definition, we've chopped along codimension 1, and in that sense, if we want to compute something, we want to compute the linear map associated to a manifold, we could chop it up and make smaller computations. And there's a multiplicativity, which has to do, it takes disjoint unions. Remember, this is a homomorphism. So it takes disjoint unions of manifolds into tensor products of vector spaces. And that's the basic multiplication that a quantum field theory satisfies. That's different from the usual sort of functors one encounters in algebraic topology, where you take spaces to abelian groups, say by homotopy groups or homology groups, where disjoint unions go over into sums. They go over into the sum of vector spaces. The characteristic property of quantum theory is you've exponentiated in some form, and you go over into products, tensor products. Now, there's more algebraic structure encoded, and here, one particular one that's of interest to us is what happens to a sphere. So if we're talking about an n-dimensional theory, then the sphere of interest is of dimension n-1, and the n-1 sphere gets attached by this map to a vector space. Now, if we just look inside the Cobordism category, inside the nonlinear manifolds, then this sphere is an algebra. So here's the picture in 1 dimension, where n is 1. The sphere we're talking about is the 0 sphere, which has 2 points. And if I draw the picture this way, it might look more familiar. So we're going to multiply 2 input spheres and get an output sphere. And the map has to be a 1 manifold. And the 1 manifold is a Cobordism that looks like this. So that's what that picture is over there, just written now with time going from left to right. And if you think of these, well, if you think of these as like indices on a matrix, you see this is really matrix multiplication. We're contracting these inner indices. And that, of course, gives an associative algebra structure, which isn't commutative. So that's the meaning of this word E1 in that case, when n is 1. What it says is that we get an associative, we can think of the zero sphere as being a kind of associative algebra inside manifolds, and that means that when we map it by the quantum field theory to vector spaces, the vector space attached to that zero-dimensional sphere is then an algebra. In 2 dimensions, we have the pair of pants, is the corresponding picture, and that gives, again, an algebra structure. And in this case, because we have a diffeomorphism of this pair of pants that interchanges the 2 inputs, then that algebra structure is, in fact, commutative. So we get a commutative algebra. Here, we don't have any diffeomorphism of this one manifold that interchanges this zero sphere and that zero sphere. So that algebra is not commutative, but we could easily draw a diagram to prove its associativity. Okay, so there's more structure encoded in a field theory. And in fact, if we do a quantum field theory where these aren't topological, this kind of structure would give the operator product kind of algebras that one encounters in quantum field theories are encoded by these kinds of pictures. Okay. So now we're going to soup this up just a little bit. We're still going to consider n-1 and n-dimensional manifolds. But in the n-dimensional manifolds, one point I didn't mention is that if we have diffeomorphic n-manifolds mediating between the n-1 manifolds, we identify them before. We just get a discrete set of morphisms. But we could consider something more sophisticated, where we consider the space of manifolds. We remember the diffeomorphisms of the manifolds that map between them. So for example, if the dimension n is 1, then we could talk about a morphism from the empty zero manifold to the empty zero manifold. For example, a circle. So a circle, in that case, is a map from the empty zero manifold to the empty zero manifold. Maybe one thing to say about the Cobordism category is that under disjoint union, the empty manifold is the identity, because the disjoint union of the empty manifold with any other manifold gives you back that manifold. So this circle, well, there's a whole space of circles. And the space of circles, if you like, it's the classifying space of the diffeomorphism group of the circle. That space is CP infinity. So if we consider a topological version, then the space we would put here of circles would be a copy of CP infinity. Then there's another one morphism, which is the disjoint union of 2 circles. We would have the whole space of those pairs of circles, which would have a product of CP infinities, but also they would intertwine. You might mix them, and so on. So we can get a richer object, this topological category. And that's been studied purely in topology. And there's a construction which takes this category, which definitely has these non-invertible arrows, and it inverts all the arrows. And what you get is actually a space. And because in this case we have disjoint union, this abelian group operation, we get the marriage of an abelian group and a space, and in topology that's called a spectrum. And the spectrum you get is a fairly recent theorem in the subject of Cobordism theory. By these spectra were conjectured, identified by Madsen and Tillman, and then the nicest proof of that is by Gladius, Madsen, Tillman, and Weiss, who identify that spectrum. So we'll just call it MT. So again, it depends, just as in the Thom case, on which kind of manifold you pick, whether it be oriented, unoriented, and so on. The simplest case is when you have framed manifolds. And if you have framed manifolds, then what you get is the sphere spectrum, just as in the Thom case. Nothing new. But in the other cases, you actually get a kind of filtration on the classical Thom spectrum. Okay, so let me make a remark here, since invertibility is a key idea in this talk, about why spaces, how they're related to invertibility. And the idea is that we can take a space. Here I said to start with a category and go to a space, but let me remark on the reverse process, how from a space we extract a category. And that's really the first construction in algebraic topology called the fundamental groupoid, where we make a category whose objects are the points of the space, and then a morphism is a parametrized path. So here we have 2 points, x and y, think of the 2 objects, and we have a red path that's a morphism from x to y. The green path is also a morphism from x to y, and we identify paths which are homotopic. That's the usual construction of the fundamental groupoid. But the main point is that the paths are invertible, you see, because if I go from x to y by the parametrization, I can just reverse time and go back from y to x. And the composition is homotopic, just by kind of reeling it in. It's homotopic to the constant path at x, which is the identity. So paths are invertible, and that's why spaces encode this kind of invertibility. Now we could go higher, if we're willing to go to higher categories, and talk about, remember the homotopy that identifies the red and the green path. And then we could remember homotopies of homotopies and on and up. So we're about to do that. Okay. So this invertibility occurs in field theory, where you might have a field theory where the image consists of invertible vector spaces and invertible linear maps. Well, what's an invertible vector space? I mean, it's invertible under the tensor product. And the only way a vector space can be invertible under tensor product is if it's one-dimensional. So invertible means that the images are all lines, the vector spaces are all lines, and the linear maps you get are all non-zero. They're all invertible. So that's why invertibility is so important. The quantum field theories where these are invertible are actually not so interesting. You definitely need the non-invertible morphisms in the Cobordism category. But these do occur in physics in two places that I know. One is in relation to anomalies, which we'll get to today. And the other one is the kind of integrand in a path integral. The exponential of a classical action could be thought of as an invertible field theory. And the nice thing about these is because they're invertible, they factor through what you get in the Cobordism category by inverting all the arrows, and that's what I just told you. It's this Madsen-Tillman business. So when you have an invertible field theory, you could study it purely in terms of classical algebraic topology as a map out of this Madsen-Tillman spectrum. Okay. So the last kind of extension of this idea of making algebra of manifolds is motivated by wanting to do extended quantum field theories. So far I've talked about theories which have invariance for n and n-1 manifolds, kind of two-tier. And now we want to go and have invariance for other manifolds in other directions. So this is something that was explored by various mathematicians, paper of Ruth Lawrence, I think Kajdan, Siegel, myself, many people in the early 90s, was very much in the air. But that idea has, over the years, gained more currency and shown up in physics too. For example, in two-dimensional theories, there are often categories that appear as part of the theories. And we could think of the category as being attached to a point in that theory. So usually we think of invariance of two manifolds and one manifold, of vector space or Hilbert space attached to a one manifold, linear maps attached to Cobordisms. But what's attached to a point is a linear category. Might be a category of D-branes, Fukaya category, etc. In four-dimensional theories and supersymmetric gauge theories, there are categories of line operators. There are categories that occur in the geometric Langland story, certainly attached to surfaces. Surfaces are two manifolds. They're, again, 2 dimensions down from 4. And then the one that's closest to this talk is the Chern-Simons theory, which really, from the beginning, had a category. So Witten introduced the Chern-Simons theory. We heard about it this morning and saw the definition in terms of the path integral. But in mathematics, that was constructed by Reshtikin and Tarayev, starting from a category of quantum group data, and that category really is what's attached to the circle. So it has different descriptions in terms of a loop group or in terms of quantum groups. And so what I mean by extended field theory really could be any of these, where we go beyond 2 tiers, but I want to mean here we go all the way down to 0-dimensional manifolds, down to points. So that's something that's completely local. And you see, whereas here, if I want to compute in an ordinary field theory, I can divide along codimension 1. If I have a field theory where I can go all the way down to 0 manifolds, then we can really divide much further. For example, if I want to compute, say I have a 2-dimensional field theory, and I want to compute what's attached to the pair of pants, then that's kind of primitive if I just know about 0 and 1 manifolds. I can't productively embed circles in there to divide it up. However, if I'm allowed to go down to points, then we can actually cut it along corners, and then we could compute it from really what happens on the disk. And so that tells us that we can start with a lot simpler information if we can cut along arbitrary codimension. So it's been a long-standing question about Chern-Simons theory in particular. Can we extend it down to points? So this has been a useful notion in topological theories, a little bit in conformal field theories and some other field theories. Of course, it would be very hard in an honest quantum field theory that depended on a metric to try to compute these things if you go to these lower codimensions. But in principle, the kind of locality tells you that it should be there. So there have been different partial results over the years about this question. By myself in the finite group case almost 20 years ago. Kevin Walker has a picture in general. We did some work there about when the gauge group is a torus, as did Kapustin and Salina. And Bartels, Douglas, and Enriquez are using ideas from conformal nets to try to attack the problem in general. So what I'll tell you is a different point of view today. So how do we encode this idea of an extended field theory where I want to attach invariance to these kinds of manifolds with corners? So we have to finally go one more step with converting manifolds into some algebraic structure. And we make a new gadget which has these manifolds with corners. And so that's going to be a category which has these higher morphisms, such as I indicated in a space. You could have homotopies of paths. And these higher morphisms in this context are manifolds with corners, like that. So, for example, the objects in this category called board N are going to be compact zero manifolds. So here's an example where we have an object Z0 consisting of 2 points. That's our friend the zero sphere. We have another object Z1 consisting of 2 points. The one morphisms are compact one manifolds whose boundaries are these zero manifolds. So for example, Y0 is a one morphism. In fact, Y0 is this cylinder. We take the zero sphere and we make the cylinder on it. So Y0 represents the identity map. That red curve, Y0, that one manifold is the identity map. On the other hand, we have another one morphism called Y1. Those are these green curves. And now there's a two morphism, which is really this square, this two manifold with corners that goes between them. And then we could go on up. So this structure organizes itself into a higher category. At least that's one way to try to organize all these different manifolds with corners. So we'll see this picture again. It's really a picture of a saddle. It's a classical move to change this picture to that picture, which are the two different manifolds there. It's a simple surgery, and that's the Cobordism that mediates that surgery. Okay, so what's the definition of one of these extended quantum field theories? It's again a morphism from board N into somewhere. But now it's a little more complicated to tell you what that somewhere is, because I have to construct some kind of linear category that could be a receptacle, a codomain for such a map. So it's easier to envision, at least heuristically, what the manifolds look like, but a little harder to think about this. Okay, so we'll leave that open. But you see, again, this encodes a lot of algebraic structure. And let's think about the three-dimensional case. What happens to a circle? Well, typically what attaches to a circle, as I indicated on the previous slide, is a linear category. On the other hand, we saw already that what's attached to a circle has this algebra structure, this E2 structure. And so the marriage of those, having an E2 structure in a category, is what's called a braided tensor category. And if you know about Chern-Simons, then you know that the category you get is, in fact, a braided tensor category. And here, what this figure indicates is when I exchange the two circles, and I do it twice, I don't get the identity. And not getting the identity is why I get something braided, and not purely commutative, which is called symmetric monoidal. All right. So there's a powerful theorem about these fully extended field theories, and basically Jacob Lurie. And what it says is that such a field theory is determined by what it does on a point. So morally, that's right, because if I know what's done on a point, then I can start to build up manifolds. And what it says, the simplest case is if we use frame manifolds, then it says that, in fact, that map not only determines the field theory, this is the set of field theories, space really of field theories, but that the image consists of what are called fully dualizable objects. So those satisfy kind of rigorous finiteness conditions that I'm not going to talk about. But really, this is a theorem about this framed Cobordism category. And what it says is it's an algebraic structure of whatever type it is that's freely generated by a single generator. That's what that theorem says. It says if I know what the image of one point is, I know everything, and there's no constraint except it has to be this fully dualizable constraint. But that constraint is built into board N. So what it says is it's the free kind of algebraic object with that dualization built in, generated by one generator. That's the kind of theorem it is. And it's really, at its heart, it has a theorem in Morse theory, because what it does, once I know what's on a point, is it builds up an arbitrary manifold by cutting it up using a Morse function. And what you have to do is check that when you cut up a manifold in different ways, you make moves, kind of Morse moves, between different Morse functions, that you get the same answer. So all the constructions in field theory have that point of view. Here, it's a theorem about contractibility of a certain space of Morse functions, actually a fairly recent theorem, but there are older theorems of Agusa, which suffice to prove this Cobordism hypothesis. And again, this finiteness is very stringent. For example, it says that the vector spaces that occur attached to n-1 manifolds are all finite dimensional. So that, from the point of view of physics, is obviously fatal, but there are ways to relax that. But in this context, they're very stringent finiteness conditions. Okay, so finally I can come and tell you now about the work I'm doing with Constantine. And so here's a theorem. And the theorem says the following. Supposing that we have one of these extended field theories in n dimensions, and let's assume that, so think of n as being even, and let's assume that the middle dimensional sphere maps to something invertible. Then what the theorem says is that everything maps to something invertible, and the whole field theory is invertible. So once the middle dimensional sphere maps to something invertible, or at least a sphere below the middle dimension, then the whole field theory is invertible. And those invertible field theories we've already seen can be studied as a piece of algebraic topology, homotopy theory, through this Madsen-Tillman construction. So it's written there. Okay, so a few remarks. So the form in which I'll say this now and sketch the proof, perhaps, is for oriented manifolds, although it's probably true for other kinds of manifolds. And again, you should think of this as a theorem about board n. So this is like in algebra. If you have a commutative ring, you can give a subset of a commutative ring, and you could say, let's invert these elements in the subset. It's called localizing the ring. And then you could see what you get. You get a new ring. And as a consequence of inverting some elements, of course, you'll find out if you play with the ring that other elements are inverted. And what this says is if we invert the middle dimensional sphere inside this algebraic structure, then everything gets inverted. But it's very hard to do that notion, even in non-commutative rings, much less this situation, to talk about this localization. So it's easier to state as a theorem about maps out, and that's in any case the form in which we'll use it. But I'll talk about it as if we could localize and just invert these elements. So just as a preview, I mean, this is a nice abstract statement, but what does it have to do with anything? So we're going to apply it to the case when we talk about four-dimensional theories. So the sphere in the middle is invertible, and the target is the braided tensor categories we just saw. And then the idea is that this theory will be related to Chern-Simons theory and will in fact give us a way of extending Chern-Simons theory down to a point. But this is an invertible field theory, so it'll play the role of an anomaly. All right, so I see time is short. And so I guess the proof sketch will be really sketchy. I think in the sixth talk, it's probably hard for me to start giving you a proof, right? All right, so what we have to prove is that everything is invertible, and that actually follows from showing that a point is invertible. So what we're going to do is prove a point is invertible. And I'm going to, in fact, tell you that a point, I told you, are oriented. So we have a plus point and a minus point. And what I want to prove is those are inverses of each other. So what that means is that their product is equal to 1. That's what it means to be inverse. But what's the product in manifolds? In Cobordism, the product is the disjoint union. The disjoint union is the zero sphere. And what's 1? 1 is the empty zero manifold. So what we have to do is show the zero manifold is the same as the empty manifold once I invert this sphere. Well, now I have to tell you how they're the same. In other words, give an isomorphism. And the isomorphism is going to be given by this disk. So this one-dimensional disk, or this interval, is a map, a Cobordism, from the empty manifold to the zero sphere. That's what F is. And if I turn F around, by time reversal, that's this dual that I said is always present in manifolds. In Cobordism, we just reverse the time on these Cobordisms. And so that F dual is the inverse isomorphism. That's the claim. That's what we have to prove. Well, how do I prove these are inverse isomorphisms? I have to show that the compositions are the identity. While this composition is, one composition is the circle, the other composition is this. And this thing I have to show is the identity. The identity are these two here. So notice that I've gone from a zero manifold, something I want to prove about zero manifolds, that this product, this zero sphere is 1. I've gone to statements about 1 manifolds. So we could keep going up. So that's one of the ideas that goes in the proof, is that we can keep pushing what we have to prove up in dimension. And somewhere we have a hypothesis. And the hypothesis halfway is that we have an invertible sphere. So that's one of the ideas. Another idea, and here let's just specialize to the case n equals 2. So we assume the circle's invertible, and we try to prove in a two-dimensional theory that everything's invertible. One of the ideas is that when you have that the circle's invertible, then the circle's also dualizable. And the data that tells you how it's dualizable becomes invertible. That's a little algebraic lemma that's quite easy to prove. And here, the circle, its dual is another circle, the oppositely oriented circle. And what gives you the dualization are these two cylinders. So in a two-dimensional field theory, it's probably familiar that this kind of cylinder gives you a bilinear pairing, and this gives you the dual pairing. And these are the duality pairings abstractly in this category of manifolds. So since these are invertible by this algebraic lemma, so is the torus when I glue them together, the product of invertibles. And now there's another lemma that says that if I have two maps, one from the identity to x, the other one from x to the identity, I know that x is invertible, and the composition in one order is the identity. In other words, it's a one-sided inverse, then it's in fact a two-sided inverse. So this is another algebraic lemma, and it basically uses the fact that when you take duals, it switches the order of the multiplication. And the dual is essentially the inverse, and that allows you to get this. And so we can now use, you see, we have to use the hypothesis somewhere. The hypothesis that the circle is invertible, I can apply this lemma to get a map from 1 to the circle. That's the disk we've already seen, called G. And then we can take a torus and puncture out a disk and view that circle as incoming. In other words, map from the circle to 1, 1 being the empty set again. And the composition of these in that order is the torus, and that we've just shown is invertible. So what this lemma allows us to know is that this disk is invertible. And once we get this disk to be invertible, then we're in pretty good shape, because now we know that the two-sphere is invertible. Because if the disk is invertible, then so is the disk read the other way, the dual of the disk, and the gluing of those is the two-sphere. But it also tells us that if I compose these in the opposite order, then that product is again the two-sphere. Well, it's the two-sphere times the identity. So it's the two-sphere disjoint union the identity, which is that cylinder. So we learn that equation. So these are equations in this algebraic construction from manifolds that you get by inverting, in this case, just the circle. Well, anyway, you can keep in that vein. That tells you kind of the main ideas. Now we've already shown the circle is invertible. That was fine. But we need to get from this picture to the identity, which is from that picture to that. And that's the saddle that we saw before when I wrote it as a square. And we want to say that saddle is an isomorphism. And so again, this is the idea of going now from 1 to 2 manifolds. And to show the saddle's an isomorphism and the inverse saddle is the dual saddle is the inverse, then we have to paste them together. We get these kinds of pictures. But you see, once we have these kinds of pictures, we already know that this cylinder, which I have here, I can, at the expense of a two-sphere, which is invertible, I can replace it by two disks. And that's what this picture does. And finally, these pictures really are the identity. They're just products. So that gives you a flavor of the proof of how it goes. It's just a funny argument interplaying the algebra and these manifolds. You're essentially using these manifolds to make this kind of algebraic argument. When you go to higher dimensions, it's a funny kind of Poincare duality, so to speak, where you start in the middle and you work both ways, but you need to get to the top, to twice the dimension, to make these arguments, to get to a place where you can make the arguments. And one of the techniques that occurs, that's really the only new idea beyond this two-dimensional case, is that now you're going to see products of spheres and balls, the classical surgeries, you're going to have to carry out, analogous to these lower dimensional surgeries. And you're going to use here the Cartesian product structure I said in the first slide appears here really using a dimensional reduction argument. That's the role of Cartesian product in Cobordisms or in field theory, is to make dimensional reduction. Okay, so that's a little bit of a proof. Okay, so let me tell you now how that kind of result can be used to learn something first about modular tensor categories, which occur in Chern-Simons theory, and then to say something at least speculatively about Chern-Simons theory. Okay, so again, if we let capital F denote the usual Chern-Simons theory, it's a topological field theory. And it's a theory of 1, 2, and 3-dimensional manifolds, which attaches to the circle this linear category. I've already said that the pictures, this pair of pants, tell you that this linear category is in fact a braided tensor category. And beyond that, it satisfies two conditions in Chern-Simons and similar field theories. One is a kind of finiteness condition. Namely, it's a semi-simple category. It has finite number of simple objects. Each of the objects has duals and so on. So there are a lot of kind of finiteness conditions that are satisfied. And then there's a non-degeneracy condition. And the non-degeneracy condition is about, usually phrased in terms of the matrix we saw this morning in Mina's talk, the matrix called S. And it's the statement that that matrix, which is defined out of that data, that matrix is invertible. Okay. So this is this 1, 2, 3 theory. And the question is, what can we do with that? How can we extend it down to points? So Reshtik and Tarayev, as I say, starting from this data, give a construction. And one of the nice things would be to fit this into the Cobordism hypothesis, which is a more general construction using the same kinds of ideas, really, about Morse functions and so on, to construct the theory that way. All right. So the first step is let's think about a braided tensor category. So that means given two objects, x and y, we have a braiding, which is a map like this. And we can consider the composition of the braiding from x tensor y to y tensor x, and then the braiding where I switch these objects, think of them in the opposite order, from y tensor x to x tensor y. Now, if I have a tensor category that's fully abelian, that's called a symmetric tensor category, then that composition is the identity. That's the symmetry. But in a braided tensor category, that's not necessarily the identity. And what we can do is look at the objects x for which it is the identity. That's a kind of center. It's a higher analog of a center, like a center of a ring, elements that commute with everything. This is a higher analog of that. And the condition that this non-degeneracy condition of this matrix being invertible is equivalent to saying that, in fact, the only objects x that satisfy that live in the center, are just multiples of a special object called 1. In other words, this category is the category of vector spaces. They're just multiples of this object. So that's an equivalent condition proved in a paper of Muger, but I think other people he cites as well. I think it's well known to people who know that kind of thing. And, okay, so remember this non-degeneracy condition. Now, braided tensor categories, I've already said, are linear categories that have this extra algebraic structure coming from this pair of pants. And the next observation is that these are actually objects of a 4 category. So if you thought 1 categories were scary, I always thought 4 categories were scary. But turns out here they are. So why is this an object of 4 category? Well, let's start here. This is the category of vector spaces, which is clearly a 1 category. So therefore, an object in here, a single vector space, well, that's a set. So that's a 0. That has category number 0. And sets have elements, so that has category number -1. So there are a lot of mathematicians who make a very good living at this level. How I fell into going positive, I have no idea, by the way. But we can consider the collection of linear categories. Vect is one example. And that's clearly a 2 category, because that's a collection of these categories. And that's where we stop, this collection of linear categories, because now we add this algebraic structure. So at the first level, we add E1. That's from here. That's this associative algebra structure. That gives us tensor categories. And that gets an extra level of category. That's 3. And if we add this commutativity, we go up 1 in dimension, that E2, that gives us 4. And that's the counting that tells us why we have a 4 category, and therefore potentially a 4-dimensional field theory. But it's important in these last two steps that we use ideas of Morita in algebra. And the idea is that if we have in this E1 step, what is a morphism between two of these algebras? Well, it's going to be a bimodule. And bimodule is the same category, but it doesn't have any algebra structure, but the algebra acts on it. The two algebras we're mapping between, they act on, then they commute. That's called a bimodule. And similarly, when we want to make E2 into a category, we have to have two more levels. And at the first level, we're going to have tensor categories, but they're going to be bimodules in a certain sense. So it's this Morita construction that gives you this extra level of category number. All right. So what this says is that a braided tensor category, if you're given sufficient finiteness to plug into the Cobordism hypothesis, this fully dualizable condition, then we can define a four-dimensional field theory. That's what the Cobordism hypothesis says. It builds up from a point. It would attach this braided tensor category to a point, and it builds up everything. In this case, we have four levels, so it builds it up through dimension 4. All right. So now in this theory, we could compute what's attached to the two-sphere. And you do that by chopping up the two-sphere using these gluing laws, essentially using manifolds with corners. And what you compute is that what's attached to the two-sphere, well, it has to be an ordinary category, because you see we started here at a point here for one manifold, and so here's where we are for two manifolds. So the two-sphere gives us an ordinary category, and that category is exactly this higher center. And I just told you that this modular condition tells you that that higher center is, to be modular, that non-degeneracy condition is exactly that it's the unit, the tensor unit vect. In particular, that's invertible under tensor product of these things. So that's exactly the situation of our theorem, where we have the middle dimensional sphere maps to something invertible. This is a two-dimensional sphere in a four-dimensional field theory. So again, I don't want to overstate this because you have to check these finiteness conditions, and that's certainly not trivial. But what this suggests then is that a modular tensor category is invertible as an object in this four category, and so it defines an invertible field theory. Okay. So again, this is a theorem in algebra about this condition of being modular, this non-degeneracy. This is another form of that condition, but it's proved using manifolds. In fact, usually these things are studied using knots. And so this is a different kind of topology that can be used to studying them, this algebraic structure of a modular tensor category or braided tensor category using four manifolds and lower. All right, so what we want to say is that this is an anomaly theory for an extension of this Chern-Simons theory, this 1, 2, 3 theory. And so I think I still have 5 minutes, right, to explain that. All right, so let me first explain what I mean by an anomalous field theory. So let's go back to thinking about n-dimensional field theories. Here we just need n and n-1 manifolds. And normally when I have an n-dimensional field theory, what it attaches to an n-manifold which is closed is a complex number. So a closed manifold maps the empty manifold to the empty manifold. The empty manifold of dimension n-1 is the unit. That maps over to the complex numbers. And a linear map from C to C is itself a complex number. So these are the partition functions that we get in a theory. And this discussion could be topological or not, doesn't matter. Now what's an anomalous field theory? It says we don't get complex numbers, but rather we get elements in a complex line, and that line in turn depends on the manifold. So to every n manifold we attach a complex line, and the partition function is now in this complex line. So it's not quite a number. All right, so these lines actually themselves obey locality, and they obey multiplicativity. The line attached to the disjoint union of manifolds is the tensor product of the lines, and these lines obey a gluing law. So that certainly wasn't obvious to me at the beginning of studying anomalies, but I learned that from a paper of Witten, I think, about M2 branes and things like that. In any case, we should think of these lines as themselves being part of a field theory. And so, you see, they have to be part of a field theory in one dimension higher, an n+1 dimensional field theory, where these lines are the vector spaces of that n+1 dimensional field theory. And we're going to ignore the numbers attached to n+1 manifolds. We're not interested in those. But this n+1 dimensional field theory, then, is invertible, because it's giving these lines. So that's why an invertible field theory gives us this anomaly. And the anomalous theory, then, is an n-dimensional theory that, so to speak, takes values in this n+1 dimensional theory. You see, to an n manifold X, in the n+1 dimensional theory, we have a vector space. It happens to be a line. And then F takes values in it. So that's why I want to say F, this anomalous theory, takes values. In fact, we can think about that concept. We don't need alpha to be invertible. We might have had that this L of X is actually a vector space, not necessarily a line. Okay. So, for example, that occurs in lots of places. Let me just mention that we could think about the chiral WZW model with its conformal blocks. You see the partition function there, when I have a conformal surface, a closed surface, two-manifold, takes values in a finite dimensional vector space, the vector space of conformal blocks. And that vector space is part of Chern-Simons theory. That's originally how it was discovered. So that's a two-dimensional theory, a conformal field theory, taking values in a three-dimensional topological field theory. And presumably there's a similar picture that holds for the very interesting superconformal field theory in 6 dimensions. And there should be an associated 7-dimensional field theory in which that takes its values. All right. And this whole notion, by the way, is a specialization. We can think of it as something called the domain wall. But I don't have time to explain that. So let me, on this final slide, explain how this fits into Chern-Simons. So again, if we start with this modular tensor category, it satisfies these finiteness conditions. We use the theorem that I sketched the proof of to show that this is invertible inside braided tensor categories, and so we get this 4-dimensional invertible theory, which could be an anomaly theory. Well, now is where this Morita idea comes. So let's just think first of an ordinary algebra A. Well, an ordinary algebra A is itself a module. I can multiply elements of A by elements of A on the left, say, and it's a one-sided module. And the same thing holds in this more complicated context where we have this braided tensor category A. It can be viewed as a one-sided module over itself. Well, in the Morita sense, that means it's a morphism from 1, the trivial algebra, to itself. So we should think of that as a one morphism in this 4 category. And there's a version of the Cobordism hypothesis that says that, again, checking these finiteness conditions, that having this morphism gives you a map of theories just in the sense that I described on the previous slide. So we get a theory thinking of A as an object, an invertible object, we get this invertible theory. 1 gives us the trivial theory. And now this module is supposed to give us a map. And that map is then a 0, 1, 2, 3-dimensional theory. So the Cobordism hypothesis immediately defines it all the way down to points. And it's a theory that takes values in alpha. Since alpha is invertible, we think of it as an anomalous field theory. So this device, using the power of the Cobordism hypothesis, would give us then this field theory. Now, what does that have to do with our original Chern-Simons? Well, the claim is that not on the point, but on 1, 2, and 3 manifolds, we can actually trivialize the anomaly. So instead of having anomalous kinds of quantities, we can get ordinary quantities and therefore recover a usual kind of 1, 2, and 3-dimensional theory. And the claim is that that will be the original Chern-Simons theory. So just to show you the first step of how that works, let's think about the circle. So what this anomaly theory does is it's a map in this 4 category or whatever from the trivial guy to what's attached to the circle by this anomaly theory alpha. But I don't want what's attached to the circle, so I want to get back to 1. And the way I do it is I use the disk. So the disk, we've already seen several times, is a map from the circle to 1. And I can use the anomaly theory, alpha, what's attached to the disk, to get this invertible map, this isomorphism from here to here. So composing with this invertible map, I can see my anomalous quantity now as a map from 1 to 1. Well, a map from 1 to 1 is going to be in this context, a category. And, well, that category you can compute then. And what you end up computing is that it is the original A as a category. And that's exactly what the Chern-Simons theory attaches to it. So you have to do that argument on 2 manifolds and 3 manifolds. There are a few little tricks. You have to be careful about which kind of manifold you use. There's a kind of cube root of unity, which is just what you expect that comes up, and so on. And so it looks like, again, we're checking a lot of pieces, but it looks like this gives an extension of Chern-Simons theory, not as a usual theory, but is an anomalous theory in the sense that what's attached to a point is a little bit funny, but nonetheless, it does extend it to be fully local. Thank you.